Friday, you spent some time looking at a podcast that described for you ray diagrams for curved mirrors. In addition to that, the mathematics of curved mirrors. You would have found when you went through that at least the mathematics was virtually identical to the mathematics for curved mirrors, which is good news. If you are comfortable with curved lenses, then you should be fairly comfortable with the mathematics of curved mirrors. The ray diagrams are a little bit different, but the good news with that is that you can actually get away without drawing any ray diagrams for mirrors if you really want to. There's patterns, and I'm going to illustrate those patterns for you right now. This is my principal axis. This is a mirror or a lens. It doesn't matter. It's a mirror or a lens. This is going to be F. This is going to be 2F. We're going to place an object in front of, let's make this a converging something, okay? Converging lens, converging mirror, whatever the case may be. We're going to put an object way out here. So our object is beyond twice the focal length right here. Again, whether it's a converging lens or a converging mirror. If you remember our ray diagrams for lenses that we drew a week or so ago, you would find that the image formed here would be, anybody remember this? The image formed here would be smaller. The image would be inverted, and the image would be real. Now, if you go back to Thursday, when you do the ray diagrams for converging mirrors, you would have found that the characteristics of the image formed from an object that was beyond 2F would be exactly the same. Smaller, inverted, and real. Now, if I move my object in a little bit to 2F, my object is now at twice the focal length. That would give us, for curved lenses, a converging curved lens. That would give me a same size image. It would give me an inverted image, and it would give me, once again, a real image. On Thursday, when you do the ray diagrams for curved mirrors, you would have found that for a converging mirror, an image produced here would be same size, inverted, and real. Same as it is for lenses. The pattern keeps going. If we move our object even further in, this time our object is between F and 2F. That would produce an image for a converging lens that was larger. It would be inverted once again, and it would be real. Well, for converging mirrors that you drew last Thursday, once again, the image is larger, inverted, and real. If I place my object for a converging lens right here, then we would find that there would be no image formed. Guess what happens when we do converging mirrors? If I place my object at that spot, the focal length, then there would be, once again, no image formed. And finally, if I place my object inside the focal length for a converging lens, it would give me an image that is larger, it is upright this time, and it is virtual. Larger, upright, and virtual. That, once again, is exactly the same as it is for converging mirrors. Now, you don't have to memorize what I just did with you. Okay, I have this memorized, and when I was spouting that off, I remember what the characteristics look like. You don't have to do that. You can draw the ray diagrams, but if you do choose to remember them, notice there are patterns here, right? It's the same for lenses as it is for mirrors, as long as it's converging. You do have to be careful, though. A converging lens is convex. A converging mirror is concave. Right, so do remember the difference between convex and concave, but as long as it's converging, they're all the same. Notice some other patterns that are forming here as well. Smaller, same size, larger. So the image gets progressively bigger, right? Until, I call this our kaboom diagram. Until kaboom, everything blows up and everything changes almost. Smaller, inverted real. Same size, inverted real. Larger, inverted real, and then it's kaboom. Now it's no longer inverted, it's upright. Now it's no longer real, it's virtual, and it's bigger. So we've got this clear pattern forming here in the first three ray diagrams, and then here's our kaboom diagram, and then completely different over here. It becomes virtual and upright. Again, whether you're talking about a converging lens or converging mirror. Now, if we've got a diverging lens or a diverging mirror, good news of this, And it doesn't matter whether you've got a lens or a mirror. It doesn't matter where you place your object. The image is always going to be the same. The image is always going to be smaller. It's always going to be upright. And it's always going to be virtual. Diverging lens, diverging mirror, doesn't really matter. As long as it's diverging, the image, no matter where you put the object, is going to be smaller, upright, and virtual. Listen, remember this. I don't care. Remember this. Or draw your ray diagrams each time. It doesn't matter to me. Just make sure that you, A, recognize that there are patterns, there are similarities between lenses and mirrors, and make sure that you can get all of these characteristics, whether it's from remembering patterns or whether it's from drawing your diagrams here. A couple other things that I want to point out here. I don't know if you noticed, but if we ever have a virtual image, there's two situations where we have a virtual image, right? Notice that a virtual image is always upright. A virtual image is always upright. Whereas a real image, the three situations where we have a real image, the real image is always inverted. Little things like that can be helpful to us sometimes. We get a question and it talks about the inverted image. It doesn't tell you whether it's real or virtual. It just says it's an inverted image. Well, we know that if it's an inverted image, it must be real. And therefore DI must be a positive value. Does that make sense? All right. What I want to do with you here now is give you some answers to the worksheet that you had, the worksheet number 16, I want to say that it was, on curved mirrors. And then we want to go over a few of those questions on curved mirrors. Again, if you were comfortable with curved lenses, these probably would have been, for the most part, okay with you. But we want to go over 2 or 3 of these just in case. Okay, let's go over 2, 5, 6, 7. Question number 2 says a 7-centimeter tall object is placed 4 centimeters in front of a diverging mirror. I want to highlight this, draw attention to this, the fact that it's a diverging mirror, because diverging mirror means that we have a negative focal length. That means right? Make sure that you get that right. If you use all the equations properly, you do everything right. If you make it positive 8.0, everything is wrong in this question. And in the multiple choice question, what you're going to get on next Wednesday's test, it's just wrong, 0 to 1, even if you do everything else right. Calculate the image distance, the image height, the magnification, and then the attributes as well. We have an object height that is 7.0 centimeters. We're going to assume the object is upright. It's placed 4 centimeters in front of a diverging mirror. DO will always be positive for us in Physics 30. The focal length we said was negative 8.0. We want to determine the image distance. We want to determine the image height. We want to determine the magnification. And then, of course, the attributes, which are going to come from those numbers. Now, I'm probably going to start off with the mirror equation here. 1 over F is equal to 1 over DO plus 1 over DI. But you know that we have 2 equations. There's the magnification equation as well. It doesn't really matter what we start with. Just like write down the equation, sub numbers in. If you get nothing out of it, then go with the other one. If you do get something out of it, great. I'm going to say for this one, 1 over negative 8.0 is equal to 1 over 4 plus 1 over DI. Now, if you want to find common denominator here, that's great. If you want to do it the shortcut way with your calculators, that's fine as well. Let's say negative 8, 1 over negative 8, minus 1 over 4, bringing the 1 over 4 to the left side by subtracting, gives us negative 0.375. Let's flip that over. We get a value of negative 2.667. So there's DI, negative 2.67 centimeters. And the fact that that's negative tells me that it's a virtual image. That's one of the 3 characteristics now. Now let's find M. Negative DI over DO. That's going to be negative 2.6667 over DO, which is 4.00, which gives me a focal length, a magnification, I should say, of 0.667. The fact that that's positive tells me that it's upright. The fact that that's smaller than 1 tells me that the image is smaller than the object. Now I do want to find the image height as well. Let's say m is equal to hi over ho. Hi is m times ho. When we do that, hi works out to be 4.67 centimeters. So we get 3 characteristics, 3 attributes. We said that it was smaller, upright, and virtual. We could have predicted that, right? We could have predicted that. If you go back to the patterns that we established here during our review at the beginning of class, if we had a diverging mirror, which is exactly what we had in question number 2, a diverging mirror always produces a smaller, upright, and virtual image. Or a diverging lens for that matter. They all produce smaller, upright, and virtual. Right? So you can get those characteristics from the numbers that we got here, or you can get it from the ray diagrams and the patterns that were formed. What was the next one, number 5 that we wanted to go over? 5? Yeah. Okay, 5 says, the inverted real image of a 6 centimeter tall candle is found to be twice as tall as the actual candle. The candle is 15 centimeters from the mirror, focal length 10 centimeters. What's the image height and the image distance here? It is a real image. A real image can only be formed if it's a converging mirror. Remember, a diverging mirror, look at my diverging mirror, always produces a virtual image. Right? We got a real image, and a real image means that it's got to be converging. So that means the focal length is positive, which is 10.0 centimeters. We say our HO is 6.00 centimeters. We're going to say that the object distance is 15. I think that's all we have, isn't it? We're going to determine the image height. I think for this one, we're going to say 1 over f is equal to 1 over do plus 1 over di again. Solve for di. Take the easy way out. 1 over 10, subtract 1 over 15, gives me a value of 0.033. Flip it over. We get di is 30. And then let's say hi over ho equals negative di over do. Could you just times 6 centimeters by 2? How come? Oh yeah, we have the magnification here. Yeah. Yeah, you're absolutely right. It says it's twice as tall as the actual candle, so the magnification is 2.00. Absolutely. Good point. How many people did it my way? How many people did it Zach's way? Good. I'm glad you did it Zach's way, because actually is a better way. If we said, let me just finish my thought on this, okay, and then we'll go back to your way, okay, the better way. Let's say hi is equal to negative di times ho over do. Solve that, and it's going to work out to be negative 12.0 centimeters. Okay, now, one thing you got to be careful of here is that this should be negative 2, actually, right? Because it's inverted, right? You got to be careful there if you said just m is equal to hi over ho, hi is equal to m times ho. That absolutely works. We get 12.0 centimeters if we made the magnification negative 2. I'm glad you spotted that. I'm glad that most other people spotted that as well. When I look at my answer key, actually, that's the way that I did it on my answer key as well, but I guess I should pay more attention to my answer key and just solve it in class here. 6 is the next one, right? Nice thing about, though, that's exact the way that I did it, though, and I wouldn't try to convince you to do it my way at all, but the nice thing about having done it that way now is that we know we're right? You do it your way, I do it a completely different way. We get the same answer. Like the odds of us getting the same answer and being wrong are pretty small, right? So that's the kind of thing where if you got time, it might be good to do it another way like that as well, if you have time. Okay, 6. 6 says a 5 centimeter tall object produces an image that's 7 centimeters behind a concave mirror. Okay, this one's tricky here. A 5 centimeter tall object. We're going to say HO is 5.00 centimeters. The image is 7 centimeters behind the concave mirror. That's going to be DI. Now, is that a real image or a virtual image? If you look into a mirror and see the image on the other side of the mirror, then that must be that's a virtual image. It has to be a virtual image. Okay? If it's on the other side of the mirror, it's a virtual image. If you think back to your array diagrams, virtual images were always on the opposite side of the mirror as the as the object was. So we're going to say that DI is negative 7.00 centimeters. Now the radius of curvature is 10. We're going to make that the focal point and make it 4.00. Now, is that a positive focal point or a negative focal point? We don't know what kind of mirror we have here, right? So how do we know what kind of focal point we have? Yeah, go ahead.
Sorry, okay, wait, so the radius of the curvature of the mirror is 4 centimeters. I'm sorry, 10 centimeters.
The radius of curvature is, oh, sorry, it shouldn't be 4 here. What's 10 divided by 2? Should be 5, right? And we do know what kind of mirror it is, right? It's a concave mirror, which is a what? Converging or diverging? Converging, so the focal point is positive 5, right? Converging, I don't care about that concave word. I want to translate that, right? Some other language that I want to use. Let's translate it to our language, which is converging or diverging. Concave mirror is converging. Now, if this is a concave lens, it would be diverging. It would make the focal point negative, but it's not. So we're going to make it positive 5.00, and we're going to find the magnification here. Magnification, HI over HO equals negative DI over DO. Don't know either one of those. So I'm going to use the lens equation, or the mirror equation first. 1 over F is equal to 1 over DO plus 1 over DI. 1 over 5 equals 1 over DO plus 1 over negative 7. Let's say 1 over 5. Let's add to that 1 over 7, because it's a negative 7. It comes over to the left side by adding. Let's flip that over. We get a DO of 2.91. And now let's find M. Negative DI, negative 7.00 over DO, which is 2.91667. Gives me a magnification of 2.40. You go back to those patterns and those ray diagrams. If we have a converging mirror and we get a virtual image, which is what we have here, right? A converging mirror, virtual image, the image has to be larger and upright. If you look at this, you see that the image is larger and upright because it's positive 2.40. So it's nice, even when you do the math here, to go back to your ray diagrams or go back to your patterns and see if they agree with each other. They do in this case, so the odds are we've done this question correctly. Finally, let's take a look at number 7. It says a 3 centimeter tall object. We're going to make that HO. Produces a virtual image that's 2 centimeters tall. We're going to say HI is 2.0 centimeters. Is it right side up or upside down? Do we know that? Virtual images are always upright. Okay? You don't remember that? That's okay. If you do remember it, that's great. If you don't, sketch the ray diagrams. It doesn't have to be perfect. Just sketch the ray diagrams and you'll find that HI will always be positive there. Now, the distance from the mirror to the image is 2.5 centimeters. It's going to be DI. Is that going to be positive DI or negative DI? tells me it's a virtual image, so it should be virtual image is a negative VI. We're going to solve for the focal length here. There's two equations. Start with whatever one you want. I'll tell you what I usually do. Unless it's really obvious to me that I'm going to use the other one, I almost always start off with this one. I'm not sure why, but it seems to work for me. Okay, so if I'm sure I'm going to use the other one, then maybe I start off with that one. Otherwise, I usually just start using this one. That's what I'm going to do here. Problem is I don't know what DO is, so I got to find that. Let's say HI over HO equals negative DI over DO. DO goes up, HO goes up, HI goes down. And it looks like this. So we're going to say negative DI, negative 2.5 times HO 3.0 divided by HI, which is 2.0. Gives me a value of positive 3.75. You get a negative here, something's wrong, because DO should always be positive for us, right? All right, so 1 over F is equal to 1 over 3.75 plus 1 over negative 2.5. 1 over 3.75, subtract 1 over 2.5, or I could have said I could have added 1 over negative 2.5. Flip that over, we get a value for F of negative 7.5. There's the focal length. Now what kind of mirror is this, converging or diverging? The negative focal length. That tells us, right? A negative focal length goes with a virtual focal point, and a virtual focal point occurs when we have a diverging lens or a diverging mirror.